All right, here we are in 8.4, ions, electron configurations, and sizes. Since we've already gone through electron configurations in the previous chapter, we're only going to focus on the sizes of ions in this particular section. So this is kind of like that question that I omitted from the last test that asked you to place the ions in order from increasing size. Well, here's the reason why ions are different sizes. First of all, cations, so your positive ions, are smaller than their parent ion. I think that should make pretty good sense. Mg2 plus is smaller than Mg. And the reason there, I mean, you're losing 2 electrons. You're giving them away. So I think it's pretty obvious why that occurs. On the opposite side of that, anions are going to be larger than their parent ions. They're gaining electrons. Okay, they're pulling electrons in. Number of protons stays the same, but they gain more electrons. This then allows them to have a full outer sublevel and a stable sublevel, and so they get a little bit larger. And the image here on the right side of the page with the sodium and chlorine is kind of showing this idea of how we can actually see the change in size of those particular atoms to ions. But here's when it gets a little bit sticky. What about ions that have the same number of electrons? Okay, let's think about this. Sodium is a great example, right? Sodium and fluorine are great examples. Because when sodium becomes an ion, it loses 1 electron. It then has 10. Fluorine will gain 1 electron, and it'll also have 10. So what happens there? They've got the same number of electrons. We call these types of elements, those that have the same amount of electrons, isoelectronic. So if 2 atoms have the same amount of electrons because of ionization, they are deemed isoelectronic. So we can look at an isoelectronic series. All 5 of these ions have exactly the same amount of electrons. But we might ask ourselves the following question. So the same number of electrons, but they've got different nuclear effects. Okay? Even though their electrons are the same, the number of protons in their nuclei actually changes, and that is what alters. That is what changes the size of the atom. So if an atom has more protons, then it's got more pull to the nucleus. So we should be able to see that aluminum, which has the same amount of electrons as an ion, as O2 negative and F negative and Mg2 plus and Na plus, but aluminum has more protons than any of those ions. And because of this, its outer electron shell, its valence shell, is pulled tighter to the nucleus. So then aluminum is actually going to be the smallest. Again, I don't think that that's the most difficult concept. It's this next one. When I ask you which would be the largest, that's a bit tricky. Many would probably point to fluorine as being the largest, but that's not the case. It's actually oxygen. Okay, oxygen has lost 2 electrons. I get it, and fluorine only loses 1, so I think that's where a lot of people say, well, fluorine's going to be a little bit bigger. But again, oxygen has less protons. Okay, and if it's got less protons and it's now losing 2 electrons, then it's got far less nuclear effect than the fluorine does. So oxygen would be bigger. All right, so that describes sizes of ions and why ions are different sizes. Now, we move on to 8.5, and we look in 8.5 as to why ions attract each other. That seems like a simple question. Well, Mr. Koenig, ions attract each other because they're oppositely charged and opposites attract. Yeah, but why don't they just like staying as their original elements? Well, individual atoms are usually pretty high in energy. So you've got, I get 2 examples up here. I got sodium and chlorine. Sodium and chlorine. 2 things that we're kind of familiar with. So if we take a look at sodium, if we took some sodium and we threw it in a kiddie pool, we would no longer have a kiddie pool. The explosion would be really impressive, and this would be really cool, and I hope at some point in time during my life I get to see this from a distance. So sodium metal, is really unstable stuff. You certainly wouldn't want to have it laying around or sitting in your hand for an extended period of time. The same actually goes for chlorine. Chlorine gas is nasty, nasty stuff. And in World War I, it was actually turned into a chemical weapon. You may have heard of mustard gas. Okay, one of the main components of mustard gas is chlorine. It seeps into your mucous membranes. It combines with the water in your body, and it forms hydrochloric acid. And you can imagine having a body full of hydrochloric acid isn't awesome. So both of these things, sodium and chlorine by themselves, are not awesome. They're not great. So they're very unstable. When we combine high energy ions, like sodium ions and chlorine ions, when we combine them, what does that do? That lowers their energy. And here's a key concept in any chemistry class. Energy down, stability up. Things that have a lot of energy aren't very stable. Okay, they run around 1,000 miles per hour. Okay, they're not very stable. It's kind of like me when I used to play basketball. I had a lot of energy. I'd fly around at 1,000 miles per hour, but be in no control whatsoever. So I had no stability. Somebody that is nice and calm and smooth on the basketball court, their energy level seems a bit down. Their stability is up. They're a little bit more stable. So that's why these two things, sodium and chlorine, will combine to form the very stable, a very simple substance, sodium chloride, or table salt. Okay, so what we need to do to figure out how these ions attract is to be able to look at some type of energy. We'll call this energy lattice energy. This is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. The lattice energy between two different ions can be calculated using an equation that looks awfully familiar. It looks like Coulomb's law. Now, we are never going to have to worry about calculating this. You're never going to have numbers to throw into this equation. But I do want you to notice something. So lattice energy equals K, it's just a proportionality constant, times Q1, Q2 over R. Now, Q1 and Q2 are the charges of the ions involved. So let's think about that. If Q1 is 1 plus, and Q2 is 1 negative, that numerator is going to equal 1 negative. Okay? Now, on the other hand, let's say instead of having 1 plus and 1 negative, like sodium chlorine, we have magnesium and oxygen, where the numerator, now Q1 is 2 positive, and Q2 is 2 negative. Now what's that numerator going to be? Well, it's going to be 4 negative. So when we have an ionic compound between two entities that are like MgO, that lose or gain 2 electrons, the lattice energy in forming that particular compound is actually 4 times higher than the lattice energy for forming the Na and the Cl. Okay, that's quite a difference. 4 times higher forming the Mg and the O. It kind of means, in a roundabout sort of way, that the magnesium and the oxygen are going to form quicker. They're going to form more reactive. They're going to be more willing to combine with one another. Okay? All right. So K is proportionality constant, Q1, Q2, the charges of the ions, and R is the shortest distance between the centers of the cations and the anions. So if we bring them closer to one another and they stay there, that is going to decrease that lattice energy. All right. Yeah. Let's take a look at what actually happens when these ionic compounds form with one another. There's a little story that can be kind of talked about when this happens, and the story takes place in 5 different steps. So there are 5 actual steps that occur when an ionic compound is formed. It's not just a negative and a positive come together. Now let's break that apart and really see what it's all about. This is advanced chemistry after all. The first thing that needs to happen is that we need to convert all of the species, so both the cation and the anion, into their gas phase. So for solids, that means to sublime the solid. So let's say we have magnesium. Okay, we take some solid magnesium, we sublime it into gaseous magnesium. That's an endothermic process. We have to actually put a lot of energy into the magnesium in order for that to happen. 150 kilojoules per mole of magnesium that we have. So that's the first step. That's the first thing that needs to happen in order for this to occur. And the second thing is the ionization energy of the metal atoms. So how much energy is it going to take to remove an electron from the metal? And it's not that much, you wouldn't think, but think about this. We're dealing with magnesium now. Okay, magnesium has a full S sublevel, so it actually takes quite a bit of energy to remove that first electron from that 3s sublevel. After that, the second ionization energy is a lot lower. So the number that you see here, the 2,180, is actually a combination of both the first and second ionization energies that allow magnesium to go to Mg2+. The third step, the dissociation of the nonmetal if needed. Right? In our example here, we're using magnesium as the metal, and let's go ahead and use oxygen as the nonmetal. Well, oxygen in its elemental form is O2. If we are going to combine magnesium with oxygen, we know that the O2 will break up into O because the resultant compound is just MgO. So how does that occur? Well, if you've got half a mole of O2 and you break it into now 1 mole of oxygen, it's going to require 247 kilojoules to do that particular process per mole of oxygen atoms. Again, that's an endothermic process. And remember, anytime you have to put energy in, this stuff doesn't happen just by itself. So right now, as it stands, as I look at this, I'm thinking, boy, this particular process is never going to happen. Because look at how much energy it requires. 150, 2,180, 247 kilojoules. My goodness, this is never going to happen. All right, step number 4. Electron affinity for the formation of X- ions in the gas phase. Again, we're working with oxygen. In step number 3, we made just oxygen atoms. But oxygen atoms aren't enough to actually bond with magnesium. We need oxygen ions. Well, how much energy is it going to take to do that? Well, in order for oxygen to become an ion, we have to add electrons. And that means we're going to, in this case, have to put in 737 kilojoules per mole. This, again, is an endothermic process. My equation's a little wrong here. Hopefully you saw that. It should be 2. It's an endothermic process. Now, all of these processes to add the electrons onto atoms are endothermic unless it's a halogen. Halogens are so close to becoming stable that that's actually an exothermic process when they receive that electron because they're so excited. All right, so that's step 4. Now step 5. Okay, so again, let's look at all the 5. So the 4 that I have up here right now, again, all endothermic. So again, I'm thinking to myself, this is never going to happen. But now, what do we have? What do we have at this point? Well, we have O2 negative, and we have Mg2 plus. There's the match made in heaven, right? So what's going to happen? Well, they're going to combine with each other. And that combination between the Mg2 plus and the O2 negative is so exothermic that it actually overrides all of the other transitions in the process. It's negative 3,916 kilojoules are released per 1 mole of magnesium oxide formed. So if we're trying to calculate, and this kind of brings us back to the thermochemistry unit, the delta H overall, the energy change overall in the formation of an ionic compound, all we have to do is add up all 5 steps. And when we do that, for this process, we come up with a negative 602 kilojoules per mole. Now, we can graphically state this on the left here, this little chart, and this chart I believe is in your book somewhere. But if we just kind of separate this out and look over here for right now, that's what we just went through. That is the transition for magnesium oxide. And we see that incredibly large lattice energy right here that brings us back down to the magnesium oxide. Here's your overall change right here. Now, compare this process to 2 elements that are plus 1, minus 1 elements that combine with each other, sodium and fluorine. So the stuff here on the right side. It is a lot less exothermic, okay? You're about negative 32 kilojoule difference from here to here for this particular process with the plus 1 and the minus 1 ions. So what's more favorable? Which one is more likely to happen? Which one is more likely to happen quicker if all conditions are the same? The plus 2 and the minus 2 ions are going to actually happen a lot quicker, a lot faster. All right, so if you want a little practice and try to work on one of these yourself. I did bring up another Born-Haber cycle. This type of diagram, by the way, is called a Born-Haber cycle for lithium and fluorine. Here's delta H overall, so if you do all of your additions correctly, your final answer should come out to that. But if you want to go ahead and try to add all those up and get that final number to see if you're doing the right process, go ahead. Oh, yeah, here's the equation that you'll need. All right.